so they were stimulated to enter the cell cycle by growth factors. So the cells were taken, they were all at one stage in the cell cycle, and then they were stimulated with growth factors to enter the cell cycle. So the cell cycle is a process whereby cells go through these various stages and eventually divide in mitosis and split into two dormant cells. So this is what's illustrated here. So basically, the cells were taken at genome and then they were stimulated to undergo this cell cycle progression and until division. Now, the next bit of information is quite crucial. It says BRDU, bromodeoxyuridine, was added to the cells and it is incorporated into newly synthesized DNA. The level of BRDU therefore gives an estimate of the percentage of cells in the S phase of the cell cycle. Okay? So when you look at a figure like this, you have to understand what's on the y-axis and on the x-axis. Very important. So on the y-axis is the measure of the percentage of BRDU positive cells. Percentage of cells in the cell cycle, which is what it tells you in the figure that you. Okay. So then it says at various times after the addition of growth factors, an anti-cyclin D antibody, which neutralizes cyclin D activity, was added to the cells. And then after a further 16 hours incubation, the percentage of BRDU was measured in each of the cell populations. Now that is a bit complicated, slightly complicated. Control cells have no anti-cyclin D antibody. So the question asks you, discuss the results of the experiment in A. Looking at A and B, what do the results of the experiment tell you about the role of cyclin D in the cell cycle? Now, having read that very carefully, if anybody would like to tell us what it shows, or what it suggests about cyclin D. Okay, well let's look at the figure then. So basically, all the blue bars refer to control cells. So that means that these cells have not had anti-cyclin D antibody, but they have had the growth factors. Okay. So you can see that they've all gone from GMOD, and they've all gone into S phase. So 100% of them are in S phase. Remember, percentage of BRDU positive cells is the percentage of cells in the S phase of the cell cycle. Or bromodeoxyuridine, remember, when DNA is made, it has to incorporate a nucleotide. And bromodeoxyuridine is a kind of a synthetic, if you like, a kind of synthetic cyclin D was added to the cells. Okay. So what does that information tell you? If you look at the red bars, what do you think that's telling you about what's happening?
Yes.
Well, look at how it works. At 10 hours, if you stimulate the cells for 10 hours and add the anti-cyclin antibody, only 10% of them go into S phase of the cell cycle. If you wait 12 hours after the addition of growth factors, maybe 15% go in. If you wait 14 hours after the addition of the growth factors, 60% go in. And if you, 14 hours. And if you wait 16 hours after the addition of the growth factors, almost 100%, 96 or so percent go into cell cycle, go into the S phase. So does that begin to clarify what might be going on here? It relates to, remember, when we discussed the cell cycle, we said that various cyclins one of which is cyclin D, are important in pushing the cells through different stages of the cell cycle. However, the important point is the cyclins are required for particular parts of the cell cycle. Okay? Different ones are required to take the cells through different parts of the cell cycle. Does that shed any light on this data? Okay. Nobody sees what this is showing? Okay, so if you're, somebody has an idea.
If all the cells are supposed to grow factor at the same time, why does the big difference between 12 and 14 hours? I mean, why does it jump from 15% to 60%?
For what, 12 and 14 hours?
From 10 to 12, it just jumps a lot.
Yeah, it jumps a lot, yeah. So they were all exposed to growth factor at the same time, but then the ones that received the antibody were given the antibody at various times after the growth factor. Okay? So you're kind of beginning to think about what's happening. So what's happening? You say there's a big change. What is the change?
Basically, going from the G1 to the S phase.
Yeah, so what's the difference between 12 and 14 hours? So, put it into words. What's the difference between that bar at 12 hours and this bar at 14 hours?
Percentage.
They're not releasing VRU, they're incorporating VRU into the DNA.
Needs antibodies as cells.
So if you wait 14 hours to add the anticyclin antibody, roughly 60 to 5% of the cells will go into the S phase. Whereas if you add the antibody after 12 hours after the growth factors, only 15% will go into the S phase. So there's a big difference. Okay? And then if you wait 16 hours after the addition of growth factors and add the anticyclin D antibody, it's hardly had any effect whatsoever. So the question is why? Why is that? I kind of already told you the answer, but yeah, exactly. The answer is really here. If you look at the cell cycle, if we say that that's probably about 24 hours, it could be longer for some cells. You can see that cyclin D here is required in this first part of the cell cycle, the G1 phase. So therefore, if you inhibit cyclin D activity at 10 or 12 hours after the addition of growth factors, you block the effect of cyclin D, and you block the entry of the majority of the cells into the S phase of the cell cycle. If you wait longer, 14 or particularly 16 hours, cyclin D has already done its job. It's no longer required in the cell cycle progression. So now the cells are more going into late G1, where cyclin E is important. Cyclin D is finished. Its activity has, its action is important over the first 14 hours after stimulation of growth factors, or maybe 12 hours, and then after that has less effect. So if you were to look at the expression of cyclin D, you'd find it's highly expressed in the first, 12 hours or so. And that's when it's needed to push the cells through G1 into S phase. So if you inhibit it in that time period, you affect the cell cycle progression. The majority of cells won't progress into the S phase. But if you wait a bit longer, it doesn't matter if you add cyclin D antibody to the cells, because cyclin D is no longer working later in G1. It's a different cyclin that's taken over to push the cells further through the cell cycle. Does everybody understand that? It's quite a difficult one. This one is quite difficult, but it does indicate a very important point, which is that different cyclins work in different stages of the cell cycle, and so for cyclin D, it's needed in the first 12 hours after stimulation with growth factors, but then the cells have gone through this G1 phase, or most of them have, and so now it's no longer needed. And you can't inhibit cell cycle progression by blocking cyclin D activity, because cyclin D activity is no longer required. They've gone through that phase. Slightly complex, I know, but this is the kind of thing you need to try and be able to understand figures for your, for this module. This is quite a difficult one, probably the most difficult I've given you. So, are there any questions on this? Do people understand what this shows? Okay, so if everybody's happy with that, we'll move on to the ones which I think are a bit easier. Is a picture I showed you last week. So I hope people already, I hope even if you consulted your notes last week, you should have the answer to that question. So would anybody like to tell me what's happening here? So which cell is the apoptotic cell?
A.
On the right. And what feature of apoptosis is it displaying? Pardon? Not really damaged, no. But letting or boiling or ruffling of the plasma membrane. Damage is not a good word when you're talking about apoptosis, because it almost suggests like it's leaky. It's not leaky. It's not really, it's changed, but it's not, although this looks very odd, in fact, none of this is leaking intracellular material, it's sealed. So this is the so-called membrane ruffling, boiling, letting that's associated with cell apoptosis. Okay, so that was quite easy. And this one's, I guess I showed you this one last week, but I don't think I showed you this, which I know that on the handout, the picture is not very good. But let's read what I said, and then you can kind of tell me what's happening. So, the picture on the handout is not colour for a start, so it doesn't look very good. So, figure 3, healthy and apoptotic lymphoid cells. B cells were stained with DNA binding dye, acridine orange, and the photo shows staining of the cell nuclei. Indicate which cells display features of an apoptotic cell. What feature or characteristic of apoptosis are the apoptotic cells displaying? So what we're looking at is staining of the DNA in the nuclei of a lymphoid cell. So, is this an apoptotic cell? Why? It has a nucleus, yeah, but this cell also has a nucleus of sorts.
Yeah, but the nucleus is shrinking, showing it's being broken down.
Okay, so you would say the cell's an apoptotic cell then? Yeah.
Perhaps.
So when you said it, say it again when you said it.
Essentially, the apoptotic cell would show that the nucleus would shrink and begin to disappear as its DNA is broken down.
That's right, that's correct.
So it may be apoptotic, but I don't be able to say for sure that the nucleus is wrong.
Well, you've given us good evidence that it is apoptotic, and it is, yes. So there's a number of cells here. What about this cell here? Yeah, again, it's been broken down. So do you know what that's called formally? This kind of feature of where the nuclear, the chromatin kind of shrinks and sometimes breaks up. Do you know what it's called? What's the term for it? Condensation. chromatin condensation. So the kind of shrinkage and condensing. And the break, sometimes it breaks up into like, they look like little tennis balls or something in the nucleus. So yeah, on this photograph, the cells that have this kind of even, kind of rounded and large nucleus, they are probably healthy cells. So that's probably a healthy cell. This one's a healthy cell. This is a healthy cell. This is a healthy cell. But then there's a number of cells here that have the DNA is shrunk, and the chromatin is shrunk, and sometimes broken up. So the nuclear DNA looks very different. So this one is obviously allophilic, this one, perhaps this one here. So that's a mixture of cells that are healthy, have a healthy nucleus, and some that have a condensed chromatin indicative of an allophilic cell. So is everybody happy with that? Okay, so the last one then, okay, so again, the picture isn't particularly good here, but there's basically two pictures here. There's an A and B, and there's quite a long description of what's going on. So we'll read it, and then we'll see. This is, I suppose, the second most difficult, maybe one I've given you, or perhaps the most difficult. I don't think it's that difficult. So it says the role of BCL2 protein in regulation of induced apoptosis in a B cell line. So again, it's a lymphoid line. So A, figure A, that's this one, shows a Western blot of BCL2 expression in untransfected B cells, lanes 1 and 2, and cells transfected with BCL2 gene, lanes 3, 4, and 5. And then B shows an agarose gel electrophoresis photograph of cellular DNA in untreated cells, in cells treated with an agent that induces apoptosis, that's lanes 2, 3, and 4. And then it says cells in lane 5, 6, 7, and 8 have also been treated with an agent that induces cell apoptosis. However, these cells have been previously transfected with the BCL2 gene, and so they express high levels of BCL2 protein as shown in A, 3, 4, and 5. Okay, so there's quite a lot of information there. And again, it's something you need to be able to begin to understand this kind of information and interpret it. So the first question is quite straightforward. It says, in A, what is your estimate of the molecular weight of BCL2 protein? Does anybody want to tell me what their estimate is? 27 what? kg stand?
Kilo.
Kilodalton. Yeah, you're not far off. I think it's 26 to 27. So you need to understand what a Western blot shows. Western blot shows essentially protein expression. And so usually you have size markers, and they're not shown, size markers are not shown on this image, but we have an indication that this is the size by the arrow here of a 21 kilodalton protein, and up here is the size of a 30 kilodalton protein. And so the big dark band here represents BCL2 expression, the level of expression of the BCL2 protein, and where it is in relation to these markers here is a rough indication of its molecular weight. So it's 27 is quite a good estimate. I think it's 26, but it's a smallish protein, 26 kilodalton. Okay, now again, looking at that, if you look at this is looking for BCL2 expression, you can see that in lanes 1 and 2, I mean, there's virtually no BCL2 expression in these cells. You can't see a band at all. In fact, they probably are very little, but it's such a little amount that you can't really visualize it on a shell like this, or on a Western blot. But you can see in 3, 4, and 5, you've got very high levels of expression, really high levels. So level of expression, just to be absolutely clear, means the amount of protein produced in the cell. The amount of protein. I don't know if you know how Western blot is done, but you basically run the protein lysates of the cells out on a gel, you transfer it to a membrane, and you use an antibody against the protein you're interested in to detect what you're interested in. So in this case, we have used an antibody to BCL2 protein. That would have bound BCL2 on protein lysate, separated according to molecular weight. And then we've used another antibody with a detection reagent to detect the expression. Okay, so we can see in lanes 1, 2, there's very little protein expression of BCL2, and lanes 3, 4, and 5, there's a very large amount. So then what's happening in B? So the question is, well, first of all, the question is, what features of an apoptotic cell can be seen in B? When comparing the photo of cellular DNA in lane 1 with lanes 2, 3, and 4. So what feature of an apoptotic cell are we looking at there? If we just answer that first question, we're looking at cellular DNA, and we're saying lane 1 is DNA from untreated cells, lanes 2, 3, and 4 are DNA from cells treated with something which induces apoptosis. So what are we looking at that is characteristic of apoptosis of cell death? Yeah, DNA degradation. So the agarose gel, if you've done one, you know that, or you may know, that the rate of migration that really depends on the molecular weight of the DNA. So if you were to isolate DNA from your normal cells, most of it comes out as a high molecular weight DNA. So there's a big, large band here. So most of the DNA will come out as a high molecular weight DNA in a normal, healthy cell, if you isolate it. But in an apoptotic cell, you can see that it's much lower molecular weight, and it seems to kind of spread over the gel, meaning that there's smaller and smaller fragments of DNA, and most of the very high molecular weight DNA is gone. So remember what we discussed this last week. What happens is, ultimately in apoptosis, an endonuclease, which you can think of as an enzyme that basically chops up DNA, is activated. So in an apoptotic cell, cellular DNA is cut into pieces. And that's obviously a very effective way of killing a cell, because it will never make RNA, it will never make protein again. Now you can't see it on your handout, but, well, you can actually, or at least you can on mine. But you can see, if you look very closely at lanes 2, 3, and 4 here, you can see that actually the DNA degradation has a kind of a regular pattern. You know, there's a kind of, it looks like ladders. So you can see that there's kind of bands at regular intervals of the gel. It's not particularly obvious, but you can see it, and it's not obvious, it's relative, there's bands. Does anybody know what those bands represent? Why we have to put in at regular intervals on the DNA? Yeah. Yeah. That's correct, yeah. So it cuts between the nucleosomes. So the arrangement of your DNA is that you have, core of 8 histone proteins, and around the histone protein core is about 150 base pairs of DNA. And then you have a linker bit of DNA, and then you've got the next nucleosome, again, with about 150 base pairs. So where the nuclease cuts between the linker, it cuts the linker DNA. So therefore, the individual cuts are about 160 to 200 base pairs intervals. So you see intervals of DNA. So it cuts between the nucleosomes, so that it's a regular cutting of that, and you see banding of about 180 base pair differences. That's a bit of detail, which if you put on the answer to the question would be very good, but I didn't really emphasize that last week, so perhaps you may not have picked that up. Okay, but then the last question is quite an important question, and it says, looking at B and comparing DNA in lanes 2, 3, 4 and DNA in lanes 5, 6, 7 and 8, what can you say about the role of BCL2 protein in regulation of apoptosis? So, now, maybe I should just clarify that a bit. So, I'm sure if I clarify it. So this gel shows, let me just explain in words what it shows. In lane 1, the cells are untreated. In lanes 2, 3, 4, 5, 6, 7 and 8, they've been treated with an agent that induces apoptosis. In lanes 2, 3 and 4, the level of BCL2 in the cells is like in lanes 1 and 2 here. Very small amount of BCL2. In lanes 5, 6, 7 and 8, the level of BCL2 in the cells is like in 3, 4 and 5 here. So it's very high levels of BCL2 protein. So all cells, 2, 3, 4, 5, 6, 7 and 8, have all been treated with an agent that induces apoptosis. The same agent, the same concentration. But the difference is that in lanes 2, 3 and 4, the cells have very low levels of BCL2, and in lanes 5, 6, 7 and 8, they have very high levels of BCL2. What do the results show? Yeah.
More BCL2 in the cells, it's more resistant to apoptosis.
Yeah. So the more BCL2 in the cells, the less likely they are to undergo apoptosis. So what does that say about BCL2? What kind of protein is it? Yes, it's an anti-apoptotic protein. In fact, it's quite remarkably anti-apoptotic. These results are actually from my lab many years ago, and it was amazing. We could put in BCL2 and protect cells from high levels of BCL2 would protect cells from all kinds of signals that induce the cells to undergo apoptosis. Now that would be a good answer to the question, but you could even make a better answer if you could remember exactly what BCL2 did. Do you remember how BCL2 works? Yeah.
It will make mitochondria not release ketosis.
Yeah, cytochrome C. Yeah. So it works by preventing release of cytochrome C from mitochondria, and that's a very strong amplification signal for apoptosis. So BCL2 is like a plug. It basically plugs the mitochondria, and it prevents them from releasing cytochrome C. And cytochrome C acts as basically a very strong apoptotic signal. So BCL2 is a survival protein, and it's again, remember, that's why it's called B-cell lymphoma gene 2, because it's involved in cancers as well. So it promotes cell survival. Okay, so if you've got all those points down, you've got it. So is everybody clear what's going on here? This is quite straightforward. You can see in lanes 5, 6, 7, and 8 that there is a bit of smearing here, but actually, if you compare with lane 1, there's very high molecular weight bands still mostly here, and it doesn't look anything like 2, 3, and 4. So even though the cells 2, 3, 4, 5, 6, 7, 8 all receive the same apoptotic signal, BCL2 effectively prevented DNA breakdown and apoptosis in the cells where it was highly expressed. Okay, so I think that basically is fine. I just would like to emphasize again, you do need to kind of try and practice looking at data, because I think what we noticed last year is that people were less good at answering questions where there was kind of data interpretation like this than they were answering kind of conventional essay type questions or short answer questions. The class as a whole found these more difficult than the conventional kind of questions. So it's worth practicing some of these to get to try and get your, it's a skill. You don't have to, once you get used to looking at scientific data and trying to interpret it, it gets easier and easier, really. But it is a skill you need to develop to do well on the module. Okay, so it's 10 past